have access to my error correcting code. I know the error channel, so I have the density matrix for my system. If I purify that into a state, there's an ambiguity in purification. And I'm just saying that, you know, if I purify the state and then look at the reduced density matrix of the environment, there's thus an ambiguity in the state of the environment. So if I compute some observables in the environment, those are not uniquely defined or well defined.
That's true, yeah. But
So-
the matrix elements look like they're going to not really change. The amount of information feels like it's not.
Right. So I think you're right that information and theoretic quantities that you can compute that don't depend on this ambiguity, right?
Or
That
unless-
aren't
yeah,
sensitive.
yeah.
So I was just trying to figure out what it was that you were like.
Well, I wasn't going much farther after that.
Okay,
Because there's
yeah.
really not that much explored.
Right.
And
see.
the stuff that has been explored involves using approximate fidelity relations, which is a can of worms I didn't want to go down.
I see. Yeah.
And other than that, I don't really know what else to say about it. It hasn't been applied as much as it should be. I just want them to get a taste.
Right. Yeah. Okay, you can go ahead and get started. Yeah, just so we have enough time for the coffee breaks.
Yeah.
Okay, so.
Thanks for waking up. Last time we started down the road of stabilizer codes. And I mentioned that in addition to giving you a code space, you get for free some compact way of defining it, which Alex already reiterated, stabilizer generators instead of like writing out a ket with exponentially many coefficients. In addition, you get a set of syndromes that partition your Hilbert space into error spaces that are labeled by some unique combination of syndromes, which are plus or minus 1. Things are mod 2, life is great, right? And I'm going to tell you a little bit more in a little more detail this structure that is induced by a given stabilizer code on the Hilbert space. I already started to do that last time, where I said that when we look at how operators are partitioned, or what kind of decomposition the stabilizer code induces on operators, I said that at least for the Pauli strings, they are split into 3 different classes. So they have either one of 3 tasks they do, each one. They either don't do anything, they preserve the code and don't do anything. And these are useful to us because these are literally the stabilizers. They can be used to index the error spaces. So this is literally what we would measure. This is what we want for something that could measure. And so when you project them into the code, you just get identity times plus 1. And then because they're literally the stabilizers, you can express them as products of powers of the stabilizer generators, which we actually measure in error correcting experiments. If they're not the stabilizers, they maybe will not respect this partitioning into the error spaces in the code space that the stabilizer code induces, and they may map you in between error spaces in some way. That way, they will flip some syndrome sign because they have mapped you to a different error space, which is labeled by different plus and minus 1s, and therefore, if you're starting with all the plus 1 state, you're going to be moving somewhere else, and you're going to anti-commute with at least 1 generator, sometimes more. And then if say they don't do that, they maintain this decomposition in the error spaces, but then they act non-trivially within the code space or within the error space. And if you project them into the code space, you get some logical here. I guess this should just be L. I didn't have this last time. If this means that because they preserve the structure, but they are themselves not stabilizers, I think the best thing we can say about them is that they just commute with all the stabilizers, but they are not themselves stabilizers. Okay. Right. And we had gone into, so we're going to study first this 3rd line and then this 4th line. We already sort of just want to review this, the 3rd line. The Paulis that map you between error spaces, I'll call E. And for each error space, you can pick one. There's many, right? Because degeneracy, there's many Paulis that take you there, but you can just pick sort of a distinguished one that you can use to sort of label that error space. And here in this table, I have my 8 error spaces. And 2 to the 3rd, aka 8 different syndrome values of the stabilizer. Each one has some error that map the code space into that error space. And I mentioned that just to hint at some future work or future lecture, that we don't have to necessarily distinguish the code space, hold it higher above all these other error spaces, because if you notice that all these error spaces are also themselves error correcting codes with the same distance as the code space. And in fact, they are themselves stabilizer error correcting codes with the same stabilizer set, except with the signs P, Q, and R put in front of the 3 stabilizer generators, such that there is no minus identity in the group, and such that the joint +1 eigenspace of these new generators multiplied by some signs is now indeed the specific error space that we have in question. Does that make sense? So just to remind you that the stabilizer group of each of these codes is this. You might think, well, who cares? Why is he talking about little signs everywhere? Well, when it comes to dynamics, when it comes to all these new modern techniques that people use, the signs start to matter. Okay, so now we'll move on to the logical Paulis. Any questions so far? Move on to the logical Paulis. And so these are things that will be code preserving, or this code error space structure preserving, but now they'll do something within the code space. And here too, we can pick some distinguished set. But I'm getting ahead of myself. So for our 4-qubit code, we have 1 logical qubit. How many logical Paulis can we have? Well, we can have the trivial one, logical identity, the logical Z and X, and then logical Y. And in general, for an NKD stabilizer codes, there will be 4 to the K different logical Paulis. I've removed the phases because it would be a global phase. And for example, we can pick the following set of Paulis to act as logical Paulis for our code. I hope, yeah, in the upper right, I've drawn the code states. And so you should see that you want to stare at that and see that I didn't make a mistake. For example, this XXII will wind up flipping 0, 0, 0, 0 to 1, 1, 0, 0. So we'll map the top first basis ket to that one. And then the XXII will map the 1, 1, 1, 1 to the 0, 0, 1, 1. So they switches them like that. And vice versa. What's more is that I've picked my basis decomposition for the error spaces in such a way that these same logical Paulis also act as logical Paulis for all the 8 error spaces. So then you want to stare at that a little longer. It's possible to do this, to pick a basis for each error space so that these Paulis implement the same Pauli that they would if they were just doing it, acting in the code space. So for example, here, XXII will take this one, put it over there. Well, that's over here. I'll take this one and put it over there. Well, that's this state. Yeah. I think it's possible in general. Yeah. Given yeah, if you don't include noise or anything else, you just have some basis decomposition, you can pick a set of Paulis that do this. Yeah. So in that sense, I would call these error transparent in the sense that they don't really care where the information is. If you act with them as a gate, the error information can be in one of these error spaces, and you would have had the same logical effect within the error space happen irrespective of where you were. Yeah. Yeah. Up to signs. Yeah. So there's been some sort of notion of error transparency in other scenarios and other contexts. I think Liang actually has a paper about that, but I would call this error transparency because you can do these same operations in each error space and get the same effect. That's sort of the original error transparency to me. This type of structure is very unique to stabilizers. Don't get carried away, okay? Bosonic codes and other codes, you lose a lot of these things. Everything, lots of stuff drops out because you don't have unitarity of your nice Paulis all the time. You don't have at least the operators that are relevant to the code. So this is a very cool and very useful structure that the stabilizer codes enforce. And in some sense, it's unique that you get all of this stuff for free just by defining a group of Paulis that doesn't contain minus identity. These are not the only logicals that I could pick. If you multiply any of these by a stabilizer, you're going to implement the same logical effect on the code, and you're not going to move around between error spaces because stabilizers don't do anything. So there are many different logical Paulis you could have picked. And how many are there actually for the 4-qubit code? For each logical Pauli, how many logical Paulis can I have that implement the same, let's say, logical X? I'm listing only 4. There may be more. I'm sorry, I'm not. Yeah. Yeah. Just now, let's just fix back to the code space. Yeah. How many ways do I have? At least 4. How many ways do I have of implementing logical X? Times the order of the stabilizer group. I can multiply by any stabilizer. How many stabilizers are there? 8. So I'm only listing 4 because I didn't want to, this would be too crowded, but I'm only multiplying by the first 4 stabilizers in my group or something. But in reality, you can have 8 different ways of implementing each logical. So there's a lot of different logicals. Okay. And given given a fixed set of logical Paulis, so let's say we pick one for each, what's called a representative or coset representative, for those of you who know what that is. Pick one representative for each of these. And so we have some fixed set of logical representatives. And we have our stabilizer group. Any code space preserving or code preserving, I don't know which one do you think I should say? Code space preserving or code preserving? Code preserving sounds like it won't do a gate. Structure preserving, stabilizer structure preserving. I hope I'm trying to be clear here. So this includes stabilizers and logicals. Any code space preserving Pauli can be written as one of our representatives times some stabilizer, some element of the stabilizer group. And this one can be trivial, so then we're reduced to just literally being a stabilizer. But if it's non-trivial, then it will implement some logical, which we've represented by our fixed four fixed representatives. And then to get to the actual Pauli string, we sometimes have to compensate to get a state and multiply by a stabilizer. Okay. Coset decomposition. I'll tell you which groups later. If you know what I'm saying about cosets, you already know which groups I'm talking about. Okay, so any code space preserving Pauli can be written as a representative of the logical Pauli group times a stabilizer. Yeah.
On the previous slide, you're making this point that the logicals act the same way in all the error subspaces. Yeah, the logicals act all the same in the error subspaces. But if you consider the error of just Z on the bottom left qubit, that wouldn't be true. Is there a reason why that error wasn't considered? Just like II. ZZ. Or sorry, IIZ.
Should be mapping you to one of these spaces. IIZI will flip the sign here and flip the sign here. So it should map you to this one. The same error space as IZII, but up to different effects. So your claim is that, oh yeah.
Okay, I guess that's related by the two state
The bottom left corner, I don't think it'll be related by stabilizers. We haven't shown how to write a general Pauli that moves you around yet. We've only shown how to write code preserving Paulis, which are not these. Okay. I'll show you how to write a general Pauli in a bit. Yeah.
There are more error spaces.
Well, let's count. How many qubits we got? 2 to the 4, 16. Each space is two-dimensional. 16 divided by 2, there should be 8. Well, that's exactly the number of syndromes. So there you go. There's 8. So these are all of them. It's another reason I did the 4-qubit code, because you can actually write them all down and not have to use font 8. Okay. So now let's combine what we've said about the things that map you between error spaces and the Paulis that we've already understood as code preserving together. So we combine notion of Pauli frame, this idea that you can pick a distinct set of errors that map you to a particular error space. We combine our distinct set of logical representatives. And we also include that we can write those up to stabilizers. Now we have a formula for any Pauli. Can be written as a particular error map, that one of the 8 error maps that we've picked to represent our 8 error spaces, times some effect within the error code space, times stabilizer. Okay. So E is some designated error, L is some designated logical, S is a stabilizer. For example, we already kind of did an example because of the good question, but let's do this one. IIYI instead of IIZI. Let's go back and see what our fixed set of representatives was. Okay, so this is a Y, so it's gonna change the label inside and it's gonna flip a sign. So we better go to an error space that has both signs and labels changed. Which label changes? Well, the bottom left again. So it's gonna be either this one or this one. Yeah, that's it. And one of them has a plus and one of them has a minus. So I'm gonna go with that one. You can verify that that's true by staring at it. Okay, there's our error representative. This maps us to the same error space as this one, but they're not equal. So let's keep going. What does this do relative to that one? Well, now we have to see which logical it implements. So we're here. There's a minus here, and there's a plus here. Relative to the X, or do they do the same thing? I think they should be an extra minus somewhere. I think. So let's go back to our designated set of logicals just to remind you which one, what is the bucket I'm supposed to be picking here. I think it should be this one. So these two map you to the same airspace, and they do the same if, well, so the product of them does a logical operation. So again, they're not correctable at the same time, just like we've seen before, but they are both detectable. And this is the net result of one trying to undo the other. It's a logical Z. They're still not equal. And we got to compensate. What do we compensate by? An element of the stabilizer group. Well, and you can kind of, if you remember the stabilizer group, you can kind of stare at it and just do it. You need an extra Z here to get to the Y. And I'm forgetting the phases. Like Sudoku. And then which generator? Well, so let's just pick this generator and see if we get away with it. These two cancel. These two cancel. So we're good at the top. And this becomes a Y. So we're good. Okay. Okay, and let's count all the different components here. The number of representative E's is how many? It's related to the question about the number of airspaces. Thank you. In general, 2 to the n minus k, because n minus k is the number of stabilizer generators. And for us, that's otherwise known as 8 because we have 4 minus 1 here. The number of representative L's. Well, that's how many logical qubits we have. So each logical qubit has identity X and Z, 4 different Paulis per logical qubit, times k times, where k is the number of logical qubits. For us, this is 4. The number of S's. How many S's do we have? We also have 8. But 2 to the n minus k also. We multiply all this together. What should we get? Remember I said any Pauli string. We should get 4 to the n, 4 to the 4. Okay. So besides saying any Pauli can be decomposed as 3 things, well, now we can go back and specialize to looking at how to decode a stabilizer code. So Alex talked about this a little bit last time, and I'm going to try to kind of interleave with him a little bit. What is the task of a decoder? Remember, a decoding is not the process of getting the syndrome. That's sort of the first step of the recovery. The decoding starts when you obtain a syndrome, and equivalently, when you narrow down which airspace you're in, then you have to figure out how to get back to the code space, how to correct. Okay, and this is only for codes where you can actually correct, not our nice 4-qubit code where you can only detect. In principle, you're going to correct. Now you have to pick which correction operation do you apply, which Pauli do you apply to correct back to go back to the code space, and you do that based on the noise model, of course. The noise model will come with probabilities of all your noise operators happening and everything. So there's PRs and probability. And but remember, you've already obtained the error space via the syndrome measurement. You obtained which error space you're in. So you know which E to put for your recovery operator. Okay. Now the question is which LNS? And that is done so by solving what's called the maximum likelihood decoding problem. And it's just saying that find me the LNS which maximize this probability of this noise, this LNS happening given E. And once you find this LNS, you plug that in and you apply that as the recovery. Okay. Now, so this is exactly the same as classical error correction. And we already know, even for the 4-qubit code, that there's quite a few combinations of LNS we can pick from. There's 4 different L's and 8 different S's. So already for 4 qubits, we don't even need to do this decoding problem because they don't correct anything. There's 32 different things we have to pick from. And in general, given an E, there are 2 to the n plus k combinations of LNS to choose from. That increases exponentially with n. So for a large enough code, we're gonna run out of memory writing down a lookup table like we did with the repetition code. It's simply not gonna fit onto our hard drive for a sufficiently large enough code. So we can't prepare ourselves ahead of time for every single E, unfortunately. So we have to do things on the fly. Like I said, this problem is very similar, and it was the NP complete complexity class of classical decoding was the proof techniques used for that, for proving that classical decoding is NP complete, was also used to show that this problem is NP complete. And in fact, this is again not my area of expertise, but many cryptographic protocols, as far as I know, I think all of the ones that are used for post-quantum for NIST in the finals at least, utilize some sort of decoding assumption, hardness of decoding assumptions. Maybe not for binary codes or qubit codes, but for other classical codes like lattice codes and stuff like that. So this is very, very hard. But quantum makes it even harder because of degeneracy. So does anybody tell me why maybe we necessarily want to do this? Maybe there's another decoding problem we should focus on. Do we need to know which S happened? Why not? Same effect. We can correct with a different SS prime. Who cares? We have the same correction still happen. And so this brings us to degenerate ML decoding, otherwise known as ML decoding in most of the quantum community, where you only maximize over the L, and now the thing you maximize is the sum over all the different S's. So now you just want to get an L, but now you have a sum in there. And things get even hairier. For example, there are cases where the dominant error is some particular L. So if you solve this problem, you get some L. And then you try to solve this problem and you get a different L. So this problem the solution to this problem tells you need to apply logical X here. And this one tells you, no, it's actually logical Z. And that's because of the accumulation of errors from the stabilizer. So there's some entropic considerations and things that I don't really understand very well. But now I hope you can see that given this type of entropic considerations that come into play with degenerate ML decoding, maybe there's some connections to statistical physics. It's sharp P complete, which is the so NP, NP is like verifying is easy, the answer. Solving, we don't know, but verifying is easy. And then sharp P is like finding the number of times you can actually have something that verifies to be true, right? It's harder. It's even harder, or probably believed to be, because they don't actually prove anything, and they just. So, and this was proved by the late Dave Poulong. And getting back to the connection to stat physics, in some cases, this sum of probabilities can be written as sum of exponentials of some minus beta times something. And that's when you get to what's called the stat-mech mapping, where you now map the problem of decoding, maximum likelihood decoding, or other decoders to a partition function of some statistical mechanical model. You can't always do this, and Alex will go through the details of, I think, a particular example of how this is done. And this has led to a very interesting subfield where there's some connections to your traditional statistical mechanics model. Okay. Okay. Let's go back to this idea that you can change the stabilizer, multiplying by a Pauli string that does a logical operation, by another stabilizer, and it'll still implement the same logical operation. So let's hold that for a second and consider where the logicals for the 4-qubit code are supported. So I've given you this set of logical representatives here. Each one is supported on at least 2 qubits, except the trivial one. Now, why is that? Well, because single qubit Paulis are errors that take you out of the code space. So those can't be logicals. So they have to be at least weight 2, and this is true in general. In fact, this is how Alex defined the distance. Each logical D is the distance. For us, it was D was 2, so at least 2 qubits, and you can see that that's the case. Sometimes you need 3. And the whole Pauli group is supported on 3 qubits, not 4. So what does this mean? So this has to do with quantum correlations. You can effectively do logical operations supported only on 3 of the 4 qubits. And that, how do you say this? If you think about it in reverse, and think about what the code can correct, it means that we can erase 1 qubit and still have the logical information. So if we consider a noise model of what's called known erasure, just erasure, a code with distance D can correct D minus 1. For us, that's just 1 qubit being erased. This implies, and it correlates with the fact that we can support our gates only on 3 qubits, that logical information is, I want to put this in quotes, storable in 3 qubits only. And what do I mean by storable? Well, I mean that if I erase everything but 1 qubit, so I do the opposite. So instead of thinking of erasure model, I do the opposite. I erase, trace out every single qubit except the bottom right of my logical state. What do I get? So this is how quantum correlations work. You can recover the information when only 1 qubit is erased. Conversely, it means there shouldn't be any information in this qubit if you just look at this qubit. and erasing all the other ones is equivalent to just looking at this qubit. So what am I supposed to get if I just look at this qubit? For any row logical. Maximum mixed state. So it's not that the information is stored. This is why I used quotes. I'm not sure how a better way to say this. Maybe somebody else can chime in, but information is not stored in only these 3 qubits, but if you only look at this one, you don't see anything. So it's distributed in some way using using quantum correlations and entanglement such that you don't actually see anything when you look at just one of these. And this is true if you erase everything else except the bottom left, top, so this idea of the correlations being such that if you look at any set of qubits where the number of qubits is d-1 or less, you won't find anything because it's stored in correlations that are greater than that. Conversely, this will mean that gates will not be able to be fully supported on the set you've erased because there's nothing there. Right? This conversely means that you can't have a single qubit logical Pauli. And in general, each logical can't be supported on d-1. It has to be supported on at least d. Okay. Because if you put it on d-1 region, well, that will automatically perform this trace, and you won't be acting on any logical information. You're acting on the maximum mixed state. Okay. Now let's go back and remember that we can move logicals around. So now if you can remember your sort of geometry, yeah. It's probably some projection or something. Yes, if you trivially just tensor in qubits, you're right. You're right. I think it's just some projection. You're right. I don't think it's full identity. Yeah. Sorry. All the examples I had in my head have identity in them. Let's be safe and just put this. I still think it's some projection, but yeah. And it doesn't have to be full rank. Fine. Yeah. But I don't want to put that because now I'm getting hesitant. But I'm gonna guess that it's just gonna be some projection. Thanks. So now let's get back to this idea that we can move logicals via stabilizers. And there's something that's a pretty interesting and cool fact that says how we can move these things around. So multiplying by an S prime may change the support of a stabilizer and move it to some other region. And another word for moving that people use is cleaning. We have a region of qubits. We have a logical that is leaking over onto this region. It's supported over there as well, but it's leaking out over here. Maybe we can clean it off this region by moving it using a stabilizer. And the cleaning lemma says that for every set of qubits M, so this just defines some set of labels of qubits that I'm going to discuss. Either you can clean So meaning that all logicals can be chosen to act outside of M. Or you can't. There exists a logical acting entirely within M. And moreover, the number of independent X and Z type Paulis, so ignoring Y, inside M, plus the number of independent X and Z generators for logical Pauli group inside everything but M is equal to 2K. So let's go over our example again with the 4-qubit code. G is this just some map that counts the number of different X and Z type logical Paulis inside M that have support only on M. Only on M. So you can split it up into only on M and only on M. Perp. So let's see. For example, let's look at all regions of M such that the number of qubits in M is just 1 for the 4-qubit code. Well, let's go back to our logicals. So pick any one of the 4 qubits and make sure that there's some logicals that, or try to partition, clean the logicals away so that you can we clean them all away from this 1 qubit, in other words? Is there a representation of the logical Pauli group that doesn't act on, say, this qubit? Well, there's one, there's Y for this one. Here's X, and here's Z. So we can clean them away from that bottom left qubit. How about top right? Here, here, and here. All right, I mean, and the other two should work as well. Why? Because remember, this corrects against 1 erasure. So looking at any 1 qubit is not gonna reveal any logical information. And so we can clean away and just not care about that qubit to begin with. So this is a situation where we can clean. And just to check, we have no X or Z type logicals inside M. We have 2 X and Z type logicals outside of M. And 2 to the 2 times K is also otherwise known as 2. Every region with M with 2 qubits. Can we clean or can we not clean? Well, so if we can't clean, there should be at least 1 logical that acts within M. Well, let's pick M to be the 2 left, the first column here. Is there a logical that acts entirely within M? Yeah, there's one right here. It already fits. So we can't clean. So things are a little dirty. There's 1 logical, but there's not all 3 of them, right? Because the Y is going to act, or if you look at the full Pauli group, you can't find one that acts on 2. You can't find a representation that acts on 2 qubits only. You have to have 3 if you want to include all of them. So that's why I say a little dirty. We can't clean it, and it's not filthy, but you know, there's this X sitting there. So we have a logical X sitting there. And on the other side, we also have, well, say that same logical X via stabilizer. So we still have 2. For any region, you can do this, and you find 1 on one side, 1 on the other. For the diagonals, for example, you find this one and this one. I don't know. I'm getting out of my league here, but I wanted to give you a taste of this also because Alex will be talking about it in more detail. Yeah. Yeah. Any one of them works. Yeah, as far as I know. I think the proof is some counting argument. I don't really know. Like, I'm not gonna be able to do it. You should ask Alex when he does this. He's gonna use this. All right, m equals 3. Can we clean? No. How filthy is it? Just very, right? The whole Pauli group can sit inside 3 qubits. I can pick a representative of each of these that sits inside all 3. So this one, well, and that one. Because M complement is the region you can erase, right? Because the code corrects against 1 erasure, you can erase 1 qubit. The complement of that is 3 qubits. Since you can erase 1 qubit, you can put all your gates onto the other part. And so all the gates can be sitting here, and so this is filthy. How many logicals we have, X and Z's? 2 inside M, 0 outside. So get 2. Okay, and this is so this is useful when it comes to geometrically local stabilizer codes. You can prove bounds on code parameters by applying this cleaning lemma. And there, geometry will come into play, and you can clean things away, and you can get only sort of string-like logical operators for 2D stabilizer geometrically local codes. And again, I want to defer to Alex on that. Okay, so let's summarize maybe what we've learned. It's kind of a bit of a maybe sporadic thing. I'm sorry about that, but it's a choice I made to give you a bigger picture. I'm going to kind of rehash what we learned and also add a little bit more group theory jargon. Yeah. For this one? This one. Which one you want to pick? No, for each distinct Pauli representative. So this one and this one are the same. You don't double count those, yeah. The reason you're not doing Y, you're only doing X and Z is because this is really counted via the symplectic representation of stabilizers as vectors in F2 to the N. The symplectic mapping. Alex talked about it a little bit, but yeah, I don't necessarily want to get into that. Can I repeat the line with the traces? So this is sort of the reverse of what I'm saying. So if you can support logicals entirely within some region M, that effectively means you can just operate on that M, and then there's the information. Sorry. And if you look at M perp, if the size of M perp is D minus 1 or less, then you can clean away all the logicals off of it. Conversely, If you look at only that region, there's nothing there left from the code. And by looking at only that region of size d-1 or less. Yes. And in terms of gates, that means you can operate on the other region because you're not doing anything in that region in some sense anyway. Okay. So let's just go over / introduce a little bit more jargon. So what is the set of code preserving Paulis? Well, that's called the normalizer. Normalizer is a group theory jargon. You define it as of something, it's a set of things in here that commute with everything in there. And in this case, the normalizer, the stabilizer group is a set of everything in the n-qubit Pauli group that commute with everything in the stabilizer. Things that preserve the syndromes. If you preserve the syndromes, you don't anti-commute with them, you only commute with them. So these are my code preserving Paulis, otherwise known as the normalizer. Inside the normalizer, you have things that don't do anything to the code and things that do logical operations, right? Well, the things that do logical operations are just removing the things that don't do anything, which is the stabilizers. Okay. And here the normalizer includes I and the stabilizers doesn't by convention. So I'm adding in, I'm tagging on an extra I. So this is, Alex used this symbol for removing elements from a set. I use minus just to make it interesting for you. So these are just all the code preserving things that actually do something within the code space. Now, what do you do? What do you do if you want to get all the logical representatives? Those are the cosets of this subgroup in this. So you do a quotient and you have a set of representatives for the logical Pauli group. This had an I, so I got to cancel the I out, so you have only the Paulis without the phases. So you get 4 to the K here. And I hope by this point all the math works out, because I've spent too many hours trying to get it to work out, especially for the subsystem case. Okay, any questions about that? Yeah. Good. So for Paulis, you can use the same word, either word, and it works out. And some people use centralizer, some people use normalizer. Think about it. Yeah. Okay. So I've done a code-centric approach. With exception of hinting about Pauli frames, I've mostly focused on this distinguished code subspace and leaving it and trying to get back into it via correction maps. The noise pushes you out, and you're trying to push the information back in, right? And you're trying to push it via a circuit. The noise is trying to push it back via some channel, and there's this push and pull. Now, there's a new modern sort of way of thinking in coding theory where it can be called loosely the circuit-centric approach, where now the noise may not be the only thing that moves you outside of the code space. Maybe you can move the logical information outside the code space. Maybe, as another example, after the noise moves you outside, maybe you don't have to get back to the same code space. Maybe you can get back to a different one. All right. I mean, the notion of Pauli frames already hints at this possibility in terms of error correction, because the error correction properties of all those other error spaces were just as good as your code space. So why move to the code space? Maybe move somewhere else. Okay, so the point is that you can do some more moving, and you not only not lose any benefits, you gain things. And this has been sort of several different the result of several different efforts fairly recently in quantum coding theory that have showed that you actually gain things. And they all kind of revolve, or at least to me, they all kind of revolve around this notion of subsystem code. So I'm going to go over what that is. Before I do that, we have to do something to our 4-qubit code. We have to make it more complicated. I'm sorry, there's no way around it. But we're still going to stick to 4 qubits. We're going to add another logical qubit. So we're going to decrease the size of the stabilizer group from 8 to 4. And turns out that we get what's called the 422 code. the distance still 2, we can sneak in another extra logical qubit and have the same detection properties. This is the smallest toric code on a torus of 4 sites. And this is the stabilizer group. And then the first index here is the logical that I've had before. And if you initialize the second logical in 0, then you get back to the code that we all might be sick of by now. But then there's these 2 other states that you can have as well that give you together 2 qubits. Okay. And for reference logical Pauli representatives, well, there's now going to be 4 to the 2. And logical X and Z for qubit 1 stay the same. Logical X and Z for qubit 2 are here. Okay. And now we want to upgrade this code to a subsystem code. What is a subsystem code? Subsystem code just takes a stabilizer code and says, well, we have some logical qubits, k equals 2 in this case. Let's just not use some of them for storage. Let's use some of them as knobs or gauge degrees of freedom that we can tune as we please while maintaining the logical information inside the qubits that are remaining to be used for logical storage. So in this case, we have 2 qubits, and I want to remember that we have 2 qubits, but not use the second one for storage and only use the first one for storage. And algebraically, this will perform a decomposition of your Hilbert space as follows. So before we had 2 qubits, we had all those other error spaces. The full space is 16 dimensional. This is 4, so this is 12. And for subsystem, we explicitly split these 2 qubits. And we pick this one for storage. And this one we call a gauge qubit. Okay. And this is a more general sort of algebraic can of worms that you can open up if you want to go down that path, and operator algebra, error correction, everything. You can start to think about algebras and subsystems and things like that. For the purposes of qubits, you just have some tensor product here that you've induced by having k qubits, and then you split it up into gauge and logicals. So how do we distinguish our gauge from our logical qubits? Well, we need another group. So we can't just do with a stabilizer group, because the stabilizer group just induces the top line. Now we need a way to split the first direct sum factor into a direct product and distinguish these from these. And that's done by picking what's called a gauge group. The gauge group G is going to be going to include the stabilizer, and it'll be a subgroup of all the code preserving maps. So all the code space preserving things, which are all the Paulis that will preserve this structure, right? We can't wreck this structure. We're just doing some extra finer grained structure within, so we only can pick out of things that preserve the structure. And right, simple examples, extreme cases. If the gauge group is just the stabilizer with some phases, the gauge group by tradition has I in it, then we didn't pick any qubits for gauge. And then we're stuck with a stabilizer code. Now, already here, you should see something non-trivial, because what is the gauge group corresponding to this stabilizer group for any P, Q, and R? It's the same. All of these have a trivial gauge group I, comma, this group, and those groups are all the same for any P, Q, and R. So if you think of stabilizer codes as gauge codes, already they are non-trivial, because a single gauge group that's I times this will not uniquely specify the signs of all the stabilizer generators. You need a stabilizer group to specify the signs. And again, you may think, why am I harping on signs? Well, it's important because when you do these dynamical circuit-centric approach techniques, the signs become important because signs will arise from measurements, so they have to be tacked along, okay? So even one already is, you should be understanding, as a non-trivial extension, slightly non-trivial, okay? Second example, all the qubits are gauge. I picked the whole centralizer. So then, sorry, normalizer. So then everything gets dragged over to this factor and there's nothing left for logical information. Probably don't want to do that either. The similarity to gauging in electromagnetism is as follows. It's only conceptual. Magnetic and electric vector potentials can be changed via gauge transformations without affecting the electric and magnetic fields. Gauge qubits can be changed and manipulated and measured without affecting the logical information. In the sense that the logical information is still going to be there. It might be moving into different corners of the Hilbert space, but will still be there, okay? Otherwise, these are not related. And the word gauge is extremely overused, but I don't have a choice. How is this done? How do you forget certain logical qubits and move them to gauge? The process of assigning some logical qubits into gauge is called gauging out. And it involves moving things into the gauge group, moving logical Paulis from the logical Pauli group into the gauge group. So given this is going to be one of three different dynamical procedures I'm going to talk about in this lecture and the next. This is the first one. And all of them will require some data. And then all of them will move from one code to another. In this case, we're going to move from a stabilizer to a gauge, to a subsystem code, sorry. I might be saying gauge code a lot. I mean subsystem code. And the data they need is a subgroup F of the normalizer. And then you can convert a stabilizer code whose gauge group is this semi-trivial group with signs into a new gauge group that now has gained these extra generators. And become what's called the center. The set of everything in here. No. The set of all elements in here commute with everything in here. Namely, the set of all elements that commute with every single element of the group, the center. Again, the set of everything in here that commutes with everything in here. Okay, so this is a map that should work for general stabilizer codes. For example, we're going to start with 422 code, and we're going to gauge out the second qubit, and that'll get us to the 4, 1, 2, 1, 4, 1, 1, 2, where now this index is split into logicals and gauge naturally, right? And the letter G I'll use for gauge. Let me do it here. So for this case, F is, what is F? Intuitively, we want to drag the second qubit into as a gauge. So its logical operations we shouldn't be using for manipulation of logical information. So what do? Well, we pick the logicals for the second qubit and just stick it into the gauge group. Yep. No. Yeah. Well, we're not looking for logical operators. We're only looking for stabilizer group. Sorry, normalizer of, yeah, I didn't define this at first because it might kind of scare people a bit, but whenever you see this, you say everything in here that commutes with everything in here. Okay. Right, so the subscript here will say what bucket I'm picking to see what commutes with everything in here. Thanks. This is not the normalizer in the full Pauli. So when there's no subscript, you assume full Pauli. Okay, so we picked this group now, and we just just crank the handle here. What was our stabilizer group of the 4-qubit code with 422? The 422 qubit code was this. The gauge group for the 422 code was just this. The new gauge group becomes just tacked on. We've tacked on now this group, and now we can rearrange it to be a little bit more symmetric looking. Now we have to take the center of this group. So what is all the set of things in here that commute with everything in here? Well, this one will commute with this, but these two will. These two will also commute with that. So that's in there. This one won't commute with this, but these two will. And then I made a typo and I forgot to kill the I factors because stabilizer groups don't have any I or -1 in them. Okay, so that's how you gauge out a qubit. The process of, right, so now we have our gauge qubits and we can do with them as we please. It won't destroy our logical information. The process of doing with them as we please, one process at least, is called fixing the gauge, right? It's setting and forgetting the qubits in some sense. You can set them to be in some in some state and forget about them. So we can gauge fix the second qubit to be in the 0 state. Bam, bam. I already showed you this. That means we are left with these two. These are now our logical states. And these are logical states of a stabilizer code. If we set and forget that we had gauge qubits to begin with, these are logical states of our favorite stabilizer. Point B, if we set the second qubit to +L, well, now we have this plus that as our logical, and this plus that as our logical one. And those also, and forgetting those as that we had gauge qubits also gives you a stabilizer code state with stabilizer group here. And this is in some sense dual kind of geometrically and then Fourier transforming to the first state. So in this way, you can see that gauge fixing for a single gauge code, a single subsystem code will give you multiple different stabilizer codes. Conversely, you can think of stabilizer codes being related to each other via some higher gauge or subsystem code via this idea that the gauge code can be fixed to either stabilizer code. Yeah.
I'm a bit confused though about like how this mapping here relates sort of doing gauge fixing. So here you start off with the stabilizer, it's mapped to the center, and now is the center the new stabilizer after you gauged out the.
Yeah, in general, yes.
And then, so.
This is a different mapping. This is the second of the 3 mappings I'm going to show you.
Okay, this is different.
This is stabilizer to gauge. This is, I'm showing here examples of gauge to stabilizer because I've fixed all the qubits in my gauge group for these examples. But in general, you don't have to fix all the gauge qubits. You can fix some of them, and then you gauge to gauge. But in the examples, you can just think of saying you can fix all the gauge qubit to some state, and then you're left. You can think of the resulting set of code states as forming a stabilizer code. And but you can do more general things. Like I said, you don't have to fix all the gauge qubits. You can leave some, and then you still have a remaining gauge group that's non-trivial. Alternatively, you can think of doing mixed state quantum computing. So you can fix your gauge qubits in a mixed state. Will that affect your logical information? No, it's still in there. It's still in the first factor. And that now you'll be doing some sort of a mixed state type quantum computing situation. Okay, so you can think of this as an advantage because maybe one of the stabilizer codes that you can gauge fix to has some nice abilities, some nice gates, and another one has some other nice gates. And so you can kind of move around in between them and do something called gauge switching and stuff. Yeah.
Related to the aerospace.
It may or may not be related to the airspaces. And I'm not joking, sometimes it's shown to be related and sometimes it's not. So it's more subtle than I can understand at this point. Advantage 2, you can use fewer qubits to obtain, you can do measurements on fewer qubits to obtain syndromes. Remember, our syndromes are eigenvalues of check operators, of stabilizer generators. But in a subsystem code, we have these additional gauge qubits, which we can measure as we please, and we don't need to worry about affecting the logical information. Well, and it turns out we can measure we can extract stabilizer information from measuring our gauge qubits because multiplication. Remember the gauge group of this code, and remember the stabilizer group. So we're after this, let's say this syndrome here. Well, we can measure, when we can obtain this syndrome by first measuring this one, and then measuring IIXX, and then multiplying the measurement outcomes. That'll give us the result of this. Everything is abelian, so we can do this. And then we can do the same with ZZ. What do we gain? We gain that we only need to wait 2 measurements. What do we lose? We need to do several of them. That's the trade-off. We've gained the ability to measure using more measurements, but each one measuring fewer weight qubits to extract error syndromes. And this idea was generalized and used by Bacon-Shor, and in a straightforward extension of this 422 code in a square or a rectangular pattern where your stabilizers are just going to be either nearest neighboring columns of X's or nearest neighboring rows of Z's, 2 nearest neighboring rows and 2 nearest neighboring columns. And the gauge group will just be generated by the little pairs inside each 2 columns and the pairs inside each row. So and these are called Bacon strips. It's a technical term. And for measuring the stabilizer generators, you just need to measure all, for a big square, you need to measure, let's say L by L square, you need to measure L of these, multiply them together, you get that. Now L is square root of N. So it's kind of a lose-gain situation. You've gained the ability to measure a giant stabilizer by using just weight 2 measurements. Kind of cool. However, the number of measurements here is extensive. Not so cool. Say you screwed up, you're multiplying a bunch of -1s and 1s. If you have a measurement error, not going to be so good. But this was a very important idea that's been now further extended in various directions by some of you, in fact. Okay, that's another advantage or another knob you can use for gauge codes. Yeah.
You have this enlarged gauge group, the group generated by IS and F, and any operation in that group does nothing to the logical qubit. So that's why I can measure the product of the two. to stabilize.
Not any operation, some operations. There's more sort of math that you can do to kind of split up the gauge group into like kind of things that don't act on the stabilizers and only on the gauge to things that only act on the gauge and not, or only on the logicals and not on the gauge and vice versa. There's a whole group theory thing that I can show you. It's in the table in my notes.
So I think I'm just confused about the fact that, so you can measure the X on the top row and X on the bottom row separately and multiply their outcomes. Why can't you do that?
Oh, sorry. You asked about the gauge group, not the normalizer.
Yeah. Just
Yeah, sorry.
So the gauge group does nothing to the logical qubit. That's why.
Yeah. Sorry. Yeah, that's right.
And then the extensiveness, what is this?
Let's imagine a family here of codes defined this way on ever larger and larger squares of size square root of n. Your stabilizers are no longer geometrically local. They're not even local, right? They're extensive, meaning their support scales with n. There's square root of n times 2 support here, or weight. So that's the bad news. The good news is you can get their outcomes by measuring weight 2 checks. Anything else? Yeah.
So what we came on that, because I would have thought that measuring the extensive stabilizer, we do exactly the same. I mean, on a quantum computer.
Well, no, in general, you'd have to measure the whole, you have to sort of entangle and get only the syndrome corresponding to the product and not the individual one. Remember those C0 gates that I used to peel off ZZI for the repetition code? I had to do one C0 gate and then another. I couldn't measure in between them because that would have given me too much information.
You don't have to place not this.
Well, you have to peel off conditional information from every qubit that's supported by the Pauli string. Otherwise, you're going to be getting more information. You're going to be getting individual products or smaller products, not the full product. You only need 1 bit. You can only get 1 bit of information and no more. And to get the right bit, you need to peel off information from every single qubit and combine it in a way that gets you only that 1 bit. So yes, you will have to do C0 gates for everything. And so in the surface code, they have these nice, checkerboard lattice, and then inside they have this ancilla that'll, do some C0s and then measure that ancilla, and that'll give you the syndrome information. So having extensive weight means you have, for a stabilizer generator, means you have extensive numbers of C0 gates. That's advantage 2. And advantage 3 has to do with physics. This gauge or subsystem codes allow you to realize more topological orders and more topological phases than you can't do with stabilizer codes. And this was done in a series of papers, again, by some of you here. And I just wanted to sort of introduce an example of where gauge subsystem codes give you a little bit more of a boost. How do you design, first of all, how do you relate to stabilizer code to a phase? Well, you take a geometrically local stabilizer code. Everybody's favorite code is here. You add up the stabilizer generator. This should be the generators, sorry, not the full group. You add up the generators into a Hamiltonian, you multiply by -1. The ground state is the surface code, and it's the code space. And this realizes, if you look at it as a phase of matter, this realizes a phase called Z2 topological order. That's great, but that's not the only phase. There's a whole bunch of different zoo phases, all right, that are described by some type of categories that describe how their low energy excitations braid and how they fuse. And you can't always get all the phases by constructing them as ground states of geometrically local stabilizer code Hamiltonians. Some phases simply cannot be obtained this way. But they can be obtained via subsystem codes. So here's another example that's very closely related that slightly extends the parameter regime of the surface code. And here's how it does so. So this is a gauge now group here, and this gauge group is just single X's in a plaquette. And the stabilizer of this is just a bunch of like non-contractible string X's and little star X's. And now, how do you construct? What do you do with gauge codes to construct sort of Hamiltonians? Well, the thing with gauge codes, like you already saw with Bacon Shore, is that the stabilizers may be extensive, may have support proportional to square root n or something. And those aren't really nice physical Hamiltonian terms. So what you do with a gauge, but subsystem codes, the physically relevant ones still have a geometrically local subsystem or gauge group. So what you do is just add up the gauge generators and you cook up a Hamiltonian for those. Now, things are not as simple anymore as they were over there. The ground state of this Hamiltonian is not really clear. And so because of this, you actually can you can play around. This has a phase diagram. You can play around with where you are in the phase diagram of this by tuning some parameters here to kind of switch you between things. This opens you up to realizing different phases with the same code. And in this case, in a sense, you're realizing something called Z2 gauge theory, which is very closely related to Z2 topological order, but not quite, because Z2 gauge theory can be in a trivial phase as well. If you crank up these single body X's and you additionally add this term to your Hamiltonian, then when you have this plus large amount of these, that's the trivial phase. If alternatively, you crank up this and that and make these relatively small, you go into the topological phase. So now you have access to phase transitions and multiple phases with the same code, while over here with this formalism, you didn't. You had one phase. Okay. Make sense? Okay. Now, I'm going to pivot a bit and discuss a whole different paradigm of quantum computing, because I think it's important for you all to get a taste of this. Yeah, 5 minutes? 10 minutes? Oh, good question. How's like the phase diagram of this Hamiltonian related to codes to gauge fixing, for example, to gauge fixing? I would say I don't know that there is a rigorous connection, but maybe the actual authors can answer that. That sounds like a cool, important question for further study to me. Infinite, right? Yeah, so it's only like kind of corners of the thing, right? So it's not like the full thing. And no, phase transitions aren't handled by gauge fixing. Okay, so let me pivot and mention another sort of application of subsystem or gauge codes by showing that a whole different quantum computing paradigm can be interpreted as a subsystem code in part. And this is called measurement-based quantum computing, or MBQC. And the thing I want you to, again, this is only to give you a taste because I can do this with 4 qubits. And I want you to think conceptually that measurement-based quantum computing, it trades space for time. So time for space. So in your usual error correction, you have some code, you have some noise, and then you do a round of correction, and you wait, and you do another round of correction, and you wait. So you're moving in time. What MBQC allows you to do is to move this whole time, is do a Wick rotation, is move this whole time-like set of rounds of correction and measurement into a state defined on one extra dimension that you can then go along and measure, which will simulate the originally time-like thing of rounds of error correction and decoding that you've had before. Okay, and this process, this wick rotation, this process of converting is possible to do with any stabilizer code. It's done via some recipes that take your stabilizer code that is involved in some time, like, standard stabilizer error correction procedure, and what's called foliating it, clusterizing and foliating it to form what's called a resource state or resource cluster state, which then you can do MBQC with. Okay. And I'm going to show you how to do this with 4 qubits. But again, the take-home message is that MBQC substitutes time for space. And this is sometimes useful in certain experimental settings where it's easier to just kind of keep creating a state than it is to do this time-like error correction. For example, in photonics. Okay, so we'll do our favorite 4-qubit code, and we're going to apply this procedure that rotates it into a resource state. So the way we do this is, first we have to do clusterization. And we're going to create a little piece of the resource state, first by taking the Z-type stabilizers, and then by taking the X-type stabilizers. That creates 2 pieces of our resource state, then that we then will foliate. The Z checks can be clusterized into a larger qubit state, multi-qubit, what's called cluster state, by adding ancilla qubits, an ancilla qubit for each generator. So first we draw our physical qubits, and we create an ancilla qubit for each generator, and making a graph that just connects the ancilla to the qubits that its corresponding check is supported on. Okay, and now in turn, this graph is used to define a cluster state. Who knows what a cluster state is? It's a very simple stabilizer state defined using a graph. So we take this graph, we ignore the distinction between data and our newly born ancillas, just treat them on the same footing. And our cluster state is defined as a stabilizer state of the following generators. For each node, we take and we create a generator and put a Z. For each node, we put X in that node. And then any neighbors of it that are connected via a link, we put a Z. Okay, and we do that here. And we do the same thing for the bottom. And this stabilized group formed by this graph, defined by this graph, defines also a stabilizer state, which is called the cluster state. Okay, we'll call this SZ, because the way we built this graph was using the Z-type checks, or S primal, they often call it. And now we come back and recall our distinction between physical or data and ancilla qubits. And now we can cook up a gauge group where we can treat we can tack on X-type operators of our two ancillas into the gauge group. I just did this, and I'm going to explain to you why this is relevant. For one, measurement of these x's, the new x's, the resulting state will be either in the code or an error space of the 412 code. And this is where the magic starts to happen. Yeah. What's up? What? Uh-huh. Yeah, then you do it again for another, you do another graph for the x's. Yeah. So you have to do it twice, because to do error correction, you have to do it twice to get X and Z type syndromes. But what's amazing here is that you get the code automatically, code of the error space in each cluster automatically. This is what I'm about to show. So this yields code or error state. So this cluster state structure respects the decomposition induced by the 412 code, even though I used only the Z-type stabilizer generators of the 412 code to define it. And this is where it's kind of cute. So let's look at it first, the Z-type. Well, so if we measure our gauge qubit in the X, and we get a, let's say, -1, so this is measurement. When we measure the other one, say it's +1, again measurement. What do we get if we multiply them? Or sorry. We measure our X, and then we recall we're in a cluster state. And by definition, a cluster state is in the +1 eigenspace of this check. So we assume we're in the cluster state, and we apply measurements on our ancillas. By assumption, we're here. By measurement, say we get -1 or +1. We multiply the two. What do we get? We get our ZZ. So we're in a code or an error space of Z type. In this case, it's -1. What about the X? And this is where it's kind of cute. We get the X for free. Oh, how? Do you see that? We are in the +1 eigenspace of this one, this one, this one. No. Sorry. This one, and then the two bottom ones that are the same. So we're in the +1 eigenspace of all four of these. What happens if we multiply all four of them? What do we get? An X for free. And this is true in general. So somewhat maybe paradoxically, we never defined this or implemented it to construct our graph. Nevertheless, the interplay of the Z-type checks and the form of the cluster state that we assume we're in yields our X's for free. And our Z checks errors, it does error detection with the Z's and yields X's for free. Yeah. Yeah. Think so. From what I remember reading the paper, this is supposed to work in general. Maybe somebody else knows more. Again, I'm not an expert in MBQC, but yeah. Okay. Thanks. So the same thing can be done for the X check, which is going to be one more ancilla and this graph.